So we're doing ready, set, go for shoot 7.1, number 11. And it says the cofunction identity states that sine of theta equals cosine 90 minus theta. So whenever they say an identity is a true statement. Like, I'll give you an identity. 5 times 1 equals 5. That's an identity. In fact, it has a very special name. It's called the multiplicative identity, meaning when I multiply the identity, it is a true statement. So whenever I multiply by 1, it's that other number. So an identity in trig it's a statement that either you've proved true or someone else has proved true. So 5 times 1 equals to 5 is something that you've proved true, because if you have 5 $1 bills, you have $5, right? Okay, so this is an identity that someone else has proved, and they're saying the co-function identity states that sine of theta equals cosine 90 minus theta, and sine of theta minus 90 equals to cosine theta. So don't ignore all this and just look at like, hey, sine could be the same as cosine. And you're like, kind of. And so we look at this and we see, oh, so again, your job as a human is to figure out where you see things that are similar and where you see things that are not the same. Okay, so then what I'm going to do is I want to write the cosine function, which is our blue function, so that it's like it looks like the red function. I'll say that again. I'm going to write a function, and it's going to be a cosine function. But when they graph it, it's going to look exactly like my sine function. So you're like, okay, we could do this. It's cosine x, right? This is what I'm starting with. It's cosine x, but I need to pick him up and move him over. I need to pick him up and shove him over or move him over. Does that make sense? I need to pick him up and move him over. So what I'm really trying to do is I want to take this, I want to take this point right here. I want to take this point right here and I want to move him. I want to move him over like this, right? I want to move him over like that. Similarly, I'd want to take this green point down here and move him over to that point right there and all the way through. I really just want to move every single point over to the right. So when I say I want to move him over to the right, who is that affecting? Now, we've been talking a lot about our functions. We have A, we have B, we have C, we have D. Who is in charge of moving to the right? Who is in charge of moving to the right? A, B, C, or D? So in case you forgot, let's write out our equation. Hold on, let me find us. So we got A cosine B x plus C plus D, right? So who is in charge of moving to the right? Yeah, you're right. It's C, the phase shift. Perfect. So I'm going to try moving him. Now, if I want to move him to the right, because he's in X land, you should all know which way we're doing this. And how much exactly to the right? Well, according to this, it's pi over 2. So, let's be wrong first. I'm going to put plus pi over 2. Oops, that's not pi. Pi over 2. That green guy did not move the right way. Look, he moved back 2. I wanted him to move forward 2, to the right 2. What was my mistake? What was my mistake? Yeah, so what should I do? How do I fix this? Very good. So remembering from a long time ago, we said that X always lives in backwards land. So if you want him to move to the right, you think, oh, plus pi over 2. But in fact, you have to make him go backwards because he's backwards. And if you now look, the green guy is on top of the red guy, meaning sine x is equal to cosine x minus pi over 2, which is exactly what they're saying here. Sine x is equal to cosine of x minus pi over 2. Now, some of you are like, but Ms. Johnson, this says 90 minus pi. What would that do to it? Let's try. So let's put cosine of pi over 2 minus x. So it's still the same guy. But in terms of what we've talked about so far, you understand him as a shift from here to here, right? This did a lot of things to it. This moved it backwards and then it flipped it, reflected it across the x-axis, which we haven't talked about reflecting across the x-axis for our cosines. So just trust the fact that these two are the same. And look, the graph says it. Purple and green are the same people. Does that make sense? So it says the cofunction identity states this is true and this is true. How does this relate to the graph in problem number 10? So problem number 10, if you remember over here, was they wanted you to do a sine graph and then you shifted it back. Now, ignore all of these. I'm going to take this pink off for just a second. If I said graph this, ignore all of the directions. Ignore all of the directions. And I said, hey, can you graph this for me? What would you choose to say? Is this a sine graph or a cosine graph? What would you choose for this to be? Sine or cosine? Yes, it's a cosine graph, right? So for those of you who've been tracking with us, cosine graphs look like a V, high, middle, low, middle, high, right? So the fact that they asked you to make it a sine graph, that was when you just chose an S and appropriately moved it whichever way you wanted. Here, you moved it back pi over 2. So what you're saying, Ms. Johnson, is I could have rewritten any of these as sine or cosine? Yeah, you could have. Like here, you could have written this. This one's actually easier as a sine, isn't it? I don't know why, but I'd prefer to keep my 0 at where he's supposed to be. Like this is a sine graph. So when they told me to graph this as cosine, I was like, okay, then I find my V and I shift him accordingly, right? Same thing with this one. If I wanted to, I could make this a cosine graph. Oh, they had us doing cosine graph by making it go this way or this way. You can also make it a sine graph by making it go middle, high, middle, low, middle. So the more comfortable you are at saying cosine is a V and sine is a S, the easier it is to understand how to graph these guys and put them as each other. And that's actually one of the things that the next lesson, which is 7.3, is going to talk about. Like, how can you write equivalent forms of cosine into sine? Like, how do you convert a function from cosine to sine or from sine to cosine? And some of you are like, why would you need to do that? In certain cases, it makes a whole lot of sense to do it. But for your purposes right now, it's a practice in understanding how everybody's related. Does that make sense? Your whole job right now in this unit, this is technically our last unit, in this unit is to feel really comfortable in terms of trig. So far in trig, I don't know if you've noticed this, but we've graphed angles, we've found the triangles, we've found the sines, we've graphed the actual functions, and last but not least, we're going to be solving equations using sine and cosine. That's kind of like one of the last things that you'll do. And then once you do this, now you're technically ready to take whatever math that you want, calculus, and other things. So once you learn trig, right, like think about like fourth grade math. In order to get to fifth grade math, you had to understand fourth grade math. And because you were in fourth grade, then you had to under third, second, first, right? You had to understand all these things. Once you get to trig, Math just gets different, not difficult. Does that make sense? So you can take calculus, you could take stats. So for those of you who are moving off into that land of calculus, be very comfortable with sine and cosine. Okay, right now you're still learning how to do all of it, but it's going to get better. Okay. Okay. So, any questions on when you're looking at a graph, be comfortable in seeing both sine and cosine. So moving on to number 12, it says, describe the relationship between the graph of f of x, the solid line, and g of x, the dotted line. Okay. Now, if you, so let's look at solid line first. Graph him. What would you name him? Would you name him as sine or cosine for number 12? Sine or cosine? And if you don't know, look at what your classmates are saying and be like, why would it be that? So yeah, you're right. A bunch of classmates put cosine. And the reason why I would put cosine is because starting at 0, I'm high, middle, low, middle, high. This is a V. Cosine is V. So down here, I'm going to write this as a cosine function. Okay. So then the next part is, let's see. Yeah, there's some amplitude on this guy. Can you tell right now what letters are being affected? What letters are you paying attention to? Think about A, B, C, and D. See if you can fill all those out. A, B, C, and D. Yeah, C is being affected. Oh, I'm sorry. Don't even talk about the dotted one yet. Sorry. Just the solid curve. Here, I'll highlight them. So we'll talk about the solid pink curve. So that's all I'm looking at. I'm just looking at the solid pink curve, which I highlighted, which it'll show up soon. So think about A. Is there an A or is it just one? Yeah, A is, no, figure out what A is. Yeah, A is 3. Very good. So A is 3 because from here to here is 3. Very subtly, you can see a 2 and the 2 is right there. So it's 1, 2, 3. So your A is 3. B, is B affected? Is B affected? Yeah, B is not affected because, Ms. Johnson, how do you know? Because normally your V goes from 0 to 2 pi, which that's where it's at right there, 0 to 2 pi. So my B is 1. So this is my period right here is 2 pi. So because 2 pi equals to BP, right? And my period is 2 pi. So 2 pi equals to B times 2 pi. So that implies that B is 1. Oops, B is 1, not B is. There you go. So then that's a 1. I don't need to write it there. Do you have a phase shift? Do you have a phase shift? Yeah, no. C is not, because it starts at 0. So I'll write because V starts at 0, no phase shift. Which I'm trying to tell you, C equals to 0. So then I just have X here, right? Did it move up and down? Did my midline move up and down? And you guys are like, no, it didn't. So there's 3 cosine X. So take all the information that we just did and now compare it to your dotted line. So because it's the same, it looks the same to me, except one of them's just pushed over. Yeah, it's okay if you write the zeros. So someone said, can we write the zeros? Absolutely. You can put plus 0, just so that you have that in your mind. Um, so I see the dotted line. The only thing that happened between your solid line and your dotted line, the amplitude A is the same, right? That amplitude is exactly the same. I still see this as cosine. I still see this as cosine, right? The period looks exactly the same because it takes the same amount of time, even though I didn't calculate it. They're both just shifted over. So my B is still the same. It is shifted over, but I don't know how much. Like, am I for sure that this is, so if this is pi, oh, these are numbers. So 1, 2, 3. Yeah, this is, there's a shift of C here, but I don't know exactly what it is. Do you guys all see? They're not giving it to you exactly. They don't want it exactly, right? So when you're doing this one, they're just asking you how, like, describe the relationship between them. So this guy is shifted over a certain amount. I don't know what it is. So I'm just going to write it as x plus c. And c is this distance here. From here to here, that's my c. Really tiny. It's going to show up right here. Are you comfortable with that? So they're just looking for an explanation of how they're related. So it's some distance. If I had to guess, I don't know. Let's see. If this is pi, yeah, they gave you a funny little graph here. So it's some units over that's less than pi. It looks like it's less than half of pi. Yeah, it's less than half of pi. It's even, I want to say it's even less than a third. I don't know. I can't be exact because they didn't give you I don't think they wanted you to know the exact number. So here, if I was going to describe the relationship, so g of x is shifted to the right c units. And that's it. Their amplitude's the same. Their period is the same. Their midline is the same. Everybody's the same. A, B, D, except for C. That was the only difference between these two. So I'm going to use this variable C. You could have not written this, and you could have come up with some number. I don't know. Maybe you said pi over 4, right? If you said, oh, Miss Johnson, I think it's pi over 4, and you had some justification for it, great. So here you can clearly tell, right? Like, let's go through the letters. Are their A's the same for number 13? Are their A's the same? Is their amplitude the same? Yes, right? Yeah, I got it too. I agree. Because the highest is the same and the lowest are the same. So A is the same. So I'm going to make a little list here. So amplitude A is the same. Okay. Let me scoot this guy over and up. Okay. What about I like to go A, C, and D. Let me see my D. Is D the same for these two? Is D the same? Yeah, D is exactly the same. If I look at that middle, it looks like it's the middle for both of them. So D is the same. Then we have a phase shift. Now these two letters, B and C, kind of depend on how you see this. So I'm going to describe to you how I see this. The solid line I still see as cosine because it starts at the top, middle, low. It goes off the graph, middle, high. But I can assume, like we've been assuming, whenever anything exits the window that we are given, it continues in that pattern. It doesn't do some wild like loop-de-loops or anything like that. It just continues. So here, even though I can't see the full V, I'm going to assume that the full V exists. Is everybody okay with that? So I still view this as cosine. Now, if you want to view this as sine, that's okay. You just look at your phase shift. It goes back. So you got middle, high, middle, low, and you don't even have another middle because this guy is so dang. I'll use the word slow. This guy is slow, right? Like look how many like V's this other guy is getting done in the same amount of time. Yeah. B is definitely affected because of the speed. Very good. So so I'm going to view this as cosine cuz I almost for some reason don't like to shift him left and right cuz there are implications that we haven't talked a lot about, but that's okay. So here, right here, I'm gonna make him my phase shift as 0. So here I'm gonna go to C. So phase shift, and this is mine. I'm talking about how I'm viewing this. Now, if you view this as sine, clearly your phase shifts are going to be different because if you started here and the other sign, the dotted sign starts here, do you see how there's a different phase shift? So I'm talking about mine. So this is the same. And I think it's a matter of efficiency for me because if I keep the phase shift the same, then there's only one variable that I need to talk about. So the only one that's being changed is B. So B is the only difference. Okay, so let me just fill this out. I'm going to make this a cosine graph, just like I said. Let's see. It's 2 cosine, right? You guys all agree with me? My B is going to go right there. I don't have a phase shift and I don't have a midline. So that is what, oh, it's not even showing up yet. Okay, so let's figure out our B. My B for the big guy, the solid guy, goes from negative 2 pi all the way to 2 pi. Now, some of you are thinking, Ms. Johnson, that's an upside down V. That's okay, because all I need is a whole cycle. And it's okay to count from bottom, so low, middle, high, middle, low. That's okay to do that. Does that make sense? So I'm going to pretend that if I continue this out, right, this would go like this, and this guy here would be at 4 pi. Does that make sense? So if I continued this all the way out like this, at the very top, it would be at 4 pi. Are you guys comfortable with me saying that? The other way to think about it is just count from bottom to bottom. So from bottom, I go from negative 2 pi to 0, and from 0 to 2 pi. This whole cycle here, for my B, is, oops, not 2 pi, is 4 pi. So that tells me that I need to set my equation as 2 pi equals BP, which in this case is 4 pi. Right? It's going to show up. Give it a second. So see how my V, if I continued it all the way out and continued, this would be at 4 pi. I can assume this is 4 pi. So, but I usually count things from whatever they gave me. So I'm not making any like counting errors here. So from negative 2 pi to 2 pi, that's 4 pi. And that completes a whole cycle. Okay. So my equation looks like this. 2 pi equals BP. And then so when I solve that, this implies that B equals to half, which that's what we said earlier. Remember, we said he was really slow. So f of x is going to be 1/2 x. Okay. Okay, can you guys do me a favor? I want you to calculate your b for g of x. Go ahead and calculate your b for g of x. So if you don't know what I'm talking about, so for those of you, I'm going to do 2 levels here. So for those of you who understand what I'm talking about, go ahead and calculate. Ignore what I'm saying right now. I'm going to try to bring other people with us. So whenever you're trying to calculate your b, you're looking for the beginning of something and the end. So I counted from bottom and counted until I got back to the bottom, because now it's a complete V. Even though it's upside down, it's okay. So here you can count this complete V from here to here. So how long is a complete, we call it period, for the dotted line? How long is that? Yeah, it's just pi. So because it's pi, then you use this equation over here to calculate that, right? So go ahead and calculate that. Here, I'll write your equation. 2 pi equals b times pi. Now solve it, and then that goes right here in front of your x. Very good. Okay, so therefore b, hopefully you guys got this as well. B equals to 2. So then this is 2x, like this. So I'm going to write 2x here. So you can clearly see the only difference is our b, which affects our period. So however you want to explain that these two are different, our amplitude was the same, our midline was the same, our phase shift was the same. The only thing that was different was, if you want to think about it, we made the solid line really slow, like we stretched them out, right? And at the same time, we made our dotted line really fast, like we squashed them together, like a spring. Can you guys imagine a spring? So my spring, when it's really slow, it's really stretched out. When he's really fast, I squish him together. So the reason why I say slow and fast is because of these coefficients. When I think about half, I think of slow. He's going to go slower than our normal cosine graph. Slower than our normal cosine graph. So let's look at these 3 just so that you guys can all see, compare them. So cosine x versus cosine, oh, we should go to. So 2 cosine x versus 2 cosine half x versus 2 cosine 2x. Okay, so this looks like a mess. It looks like a crazy mess, okay? So what I want to do is I only want to compare our original function, which is our, like, they call them parent functions. So 2 cosine x, that's our original blue function, compared to our black function, which is our slow function. Do you almost see like how I pulled the blue one apart? And that's how I got this black one. I pulled it from the ends right here. And that's how I got that one. And then if I compare it to my red function, I squished them together, like, kind of like how, I don't know, I was thinking when I pack, I like squash my clothes as tightly as can be, right? So he's much faster. So think about fast and slow. I would assume that half makes something slower because I'm only getting half the work done in the same amount of time, versus 2x, I'm getting like twice the amount of work done. So if I put all of these together, I know it looks kind of like a mess, but it kind of is like really pretty because it has like this really nice symmetry kind of thing. So if you can you look at 1v? Look at 1v. How do I do this? What do I do again? I think it's this. 0, 2 pi. I want you to look at one thing. I do it like this. I have to do it like. Right. You don't have to pay attention to this. This is me just trying to make your lives easier. Is that right? It's not giving me from 0 to 2 pi. I think I did something wrong. maybe this. I can't remember. You want my other target? Sorry, I'm trying to remember how to do. It can be 12. Point. I just leave it alone. That's not doing it. All right. So can you imagine one here? I'll just trace it. That'll be my little thing. I'm going to do my best to trace this guy. So, so look at the one. I should keep them the same color. So this is the blue guy. And then this is the and then this is the red guy. Oops. Okay. So if I can, like, just turn these off for just a second. I just want to look at these, right? So look how, like, in one thing of one V takes, look how short it is for red. It takes them that many seconds, let's just say, versus my blue guy versus the black one, right? Like, wow. Like, so that's what I mean by, these coefficients. That's what it does to it. It stretches it out or squishes it together. Okay, so is that okay? Let's see. That's good. So you should be able to look at this and be like, boom, boom, boom. This is the difference between them. Okay.